is the CEO of Swayaatt. He has been researching autonomous navigation, focusing on reinforcement learning and motion planning for 11 years. Most recently, he has been developing autonomous driving technology that works in traffic with highly stochastic and dynamics. His secondary research focus is on enabling autonomous vehicles to perceive their environment using only off-the-shelf cameras. So Sanjeev holds a BTech in electrical engineering from IIT Roorkee in 2011 and attended University of Alberta from 2012 to 14 for his MSc in computing science, where his advisor was Professor Richard S. Sutton. From September 2011 to April, he was a research assistant to Professor Zvi Stiller. Excuse me if I am not able to pronounce this name correctly. At Ariel University in Israel. They developed motion planning algorithms to enable robots to navigate at high speeds in cluttered environments. So, without any further ado, let's welcome Mr. Sharma to give a talk on his research.
Thank you so much, Dr. Ashish Saini, for inviting me to this talk and for the introduction. So, hello everyone. I'm Sanjeev. I'm the founder of Swayaatt Robots. At Swayaatt, we are, as Dr. Ashish already mentioned, that at Swayaatt we are developing autonomous train technology that works in highly stochastic traffic dynamics and in both the structured and unstructured environment conditions. And furthermore, one of our secondary goals is also to enable autonomous vehicles to perceive using only off-the-shelf cameras without requiring lidars or radars to reduce the price of technology for the end customer. So this talk is an introduction to reinforcement learning with examples of real-world applications and highlights of some of our research in RL for motion planning and decision making under uncertainty, and also to solve and also various control problem highlights again in the context of autonomous driving to enable autonomous driving in stochastic traffic. So in a nutshell, reinforcement learning is a branch of machine learning that allows machines to solve the sequential decision-making problem. So there are three major types of machine learning algorithms. These are supervised, unsupervised, and reinforcement algorithms. And supervised learning algorithms learn by examples. For example, the data here consists of input samples and their corresponding target values or labels. And the goal of the goal of the learning system is to compute a function that maps the input samples to their desired outcome or the target labels. In unsupervised learning, so unsupervised learning concerns mostly with finding the hidden underlying structure in the data. And also, for example, one of the goals of for example, unsupervised learning in the context of computer vision or image classification or segmentation is to be able to compute such labels automatically to automatically determine the number of labels, as well as to simultaneously learn a function to compute them and assign those labels to the input samples or pixels or whatever the problem that we are solving. So the data here just consists of samples with no outcome, no target values or no labels. Then there is reinforcement learning where the learning actually happens via interaction of what we call an RL agent with its environment. So this is a learning by experience via trial and error. And the data here consists of trajectories of the experience of the interaction of the agent with its environment. So the goal in reinforcement learning is to be able to learn a policy that allows an RL agent to make decisions, to take actions that are sequentially optimal. So it's a branch of a machine learning or mathematics that allows machines to be able to learn to solve the sequential decision making problems. So here's a classical example of what supervised learning is in both classical supervised learning, classical and deep supervised learning. So assume that we have an input image where the goal is to classify, let's suppose, every pixel in this image in road and environment pixels. So a typical machine learning algorithm will proceed with classifying each of the pixels independently, where perhaps we'll select a small region around each pixel. So this patch is centered on the pixel, and perhaps we have ground truth labels for many such patches. And then instead of directly feeding these patches to a machine learning system, a feature is constructed, a nonlinear feature representation is constructed on top of these patches. And then these feature vectors are fed to a machine learning algorithm, which then learns to map the feature vectors to the labels road and environment. And when a new image comes, again, we repeat the same process. We select each of the pixels, maybe select a patch around that pixel, construct a feature representation on top of that patch, feed it to the machine learning algorithm, which will then be able to classify it as road or non-road based on the learned functional mapping that is learned from the training data. In deep learning, on the other hand, this entire block of feature engineering and learning this function mapping is replaced by a deep neural network. In deep learning, again, we can again sort of divide the image into patches, and we can feed each patch at a time to a deep learning system, but that would be very inefficient approach. So in deep learning, we can directly feed this entire image to a network, and the network would be able to build a representation that is appropriate to solve the problem, perhaps a classification problem. So it would automatically build this, complex representation that is really good at solving such problems. At the same time, it will also learn the mapping function. So this entire block of feature construction, sorry. I'm just not able to get rid of this tab. Sorry about that. Sure. So in deep learning, this entire block of feature engineering and this function map learning is replaced by deep neural network. If we talk about unsupervised learning, then again, the same thing applies over here. We have an input image, and again, let's assume that the goal is to segment this image into various regions. But the challenge here is that we don't have the number of labels or the type of labels that should be assigned to each of the pixel. So the goal of an unsupervised learning system would be to learn the number of labels as well as learn a functional mapping to assign those labels to each of the pixels in an image. And here again, we again follow the same standard procedure. Maybe we'll build a patch around each of the pixels. We'll construct a nonlinear feature representation on top of those patches. Those patches will be fed to the system, and the system will decide what the label should be, and then compute those labels for each of the patches centered on the pixel. In deep unsupervised learning, on the other hand, we can directly feed the input image to a deep neural network. And in an ideal scenario, this system would be able to learn the number of labels as well as assign those labels to each of the pixels in an image. But usually this is not so ideal in practice. Usually the end, there's a number of labels or the number of segments is usually a hyperparameter. For example, consider the classical clustering algorithms in machine learning. So in any clustering algorithm, we eventually have to provide the number of labels or the number of clusters or the number of segments if we are using those algorithms for image segmentation tasks. So, for example, deep learning system. For example, this is one of the demo where we have built, an algorithm that both segments the road, segments the image into road and environment region, as well as simultaneously detect obstacles. So this is the world's fastest deep network system for doing such kind of operations. So if you consider typical YOLO or mass car CNN, it is 10 times faster than YOLO for obstacle detection, roughly 40 times faster than mass car CNN. And it is up to around 20 times faster than typical semantic segmentation frameworks. So this is what deep supervised learning can achieve. We can segment fairly complex images with very, very high accuracy. However, such tasks are static in a sense that the decisions made by a network on per pixel basis do not translate to the next image, or they do not have any future consequences. For example, if the network made an error, that would be a suboptimal performance. But again, we can correct that via learning by feeding it more training examples, and the network would be able to learn against those training examples and correct that performance. But there's no future consequences in terms of the decisions that is made by the neural network on per pixel basis. So we call such problems like static problem in a sense that they do not have any future consequences. Reinforcement learning, on the other hand, is a branch of mathematics that allows machines to learn to solve the sequential decision-making problems. That is a kind of problems where the actions taken or the decisions made have both the immediate as well as the future consequences. And the goal of the goal of such a system would be to learn to make to learn to make decisions that are sequentially optimal, as opposed to other machine learning paradigms where the learning system optimizes its performance against a fixed target or a static error function on per pixel basis. So in reinforcement learning, we try to we actually so reinforcement is a branch of basically ML or mathematics that facilitates this sequential decision making problem. Like it allows machines to learn to solve the sequential decision making problems, which are both the immediate as well as the future consequences. So as opposed to in other machine learning paradigms, the learning happens via natural interaction of an RL agent with its environment. And these interactions provide the agent with feedbacks or reward signals which help shape the behavior policy of an agent. So a policy is simply a function that governs the behavior of an agent in an environment. So using these reward signals or these reinforcements or feedbacks, the reinforcement learning algorithms try to learn or optimize the policy for the RL agent. So this is what an agent environment interaction model looks like. So in reinforcement learning settings, we have an agent and we have an environment. So the agent continuously interacts with this environment. So at each time step, agent observes the state of the environment, which is represented by ST. So agent observes the state of the environment or finds itself in a state ST. In that state, using its policy, which maps states to actions, it selects a particular action at a particular time step t denoted by AT. When this action is executed, it results into a transition in the it makes a transition to a next state. It changes something in the environment, and that is why the agent has a new observation of the state of the environment. So agent finds itself in a new state ST plus 1. And as a result of this transition from state ST to state ST plus 1, environment provides a reward signal RT plus 1 to the RL agent. And then the process continues. Again, in state ST plus 1, agent will again query its policy to select action AT plus 1 and get a reward signal RT plus 2. And the process repeats. So in a nutshell, at every time step, agent is in some state. In that state, it takes certain action using its policy. The execution of that action results agent transitioning to a new state, ST plus 1. And that transitioning provides a feedback to the RL agent, which we call the reward signal, which is noted by RT plus 1. And the reinforcement learning algorithms uses this reward signal to optimize or to improve the policy of the RL agent so that it can capture more and more higher rewards or returns from the environment. So we will define like what are the components of an RL agent, like what is learned in the reinforcement learning process. So agent has three components: of policy, through which it acts in an environment. So formally, policy is a mapping from states to actions. A policy can be stochastic, a policy can be deterministic. If a policy is deterministic, then the mapping from states to action would be deterministic. If the policy is stochastic, then the mapping, then the policy will map a state action pair to a value between 0 and 1, which is the probability of taking a particular action in a particular state. And policy governs the behavior of an RL agent in an environment. Then we have a value function. So value function is always a function of a policy. In a nutshell, what value function tells us is that it stores the value of either the state or the state action pair. So in a nutshell, a value function or a value of a state S tells us how good it is to be in that particular state, given that we are following a policy pi. Similarly, the state action value function for a state action pair S and A tells us how good it is to be for an RL agent to be in a state and take action A, and thereafter follow the policy pi for action selection. So value functions are measure of goodness of the state or state action pairs. The third component of the RL agent is the model. So a model tells the RL agent how the environment or the world behaves. So typically a world model would incorporate a reward function that will tell the agent how the rewards are generated in the environment. And it will also incorporate the transition dynamics as to, for example, if an agent takes a action A in state S, what's the probability of transitioning to next possible state? So this transitioning model will sort of provide the probability distribution over the next states resulting from taking an action AT in state ST. So this is what a world model encodes. And if the agent has a world model, then it can use that model to look ahead into the future, to look into the future consequences of the action that it is taking. And depending on the RL algorithm that we are using, for example, there are different kinds of RL algorithms. These algorithms either learn a policy, or they learn a value function, or they learn a combination of those. They can also learn simultaneously model as well. There are both model-based and model-free RL algorithms, which we'll be discussing later in this slide. So coming back to the interaction model, we discussed earlier that the agent continuously interacts with this environment and gets and gets the reward signal. So here we will define two terms that will facilitate the rest of our discussion. So one is the return, the discounted return, and the other is a discount factor. So using these reward signals, the RL algorithms try to optimize the RL agent's policy. And the goal of the RL agent is to maximize the return or the discounted return. So the discounted return is defined as sum of all future discounted reward signals, which can be concisely represented by the summation. And the gamma is known as the discount factor, which takes a value between 0 and 1. So rather than maximizing the immediate reward, RL agent's task is to maximize the return or the discounted return. Because if the RL agent just tries to maximize the current reward, then it may lead to suboptimal performance, because in that sense, the RL agent would be greedy with respect to the immediate rewards and won't take the future consequences of its action into account while making decisions. So here's a good example, like for example, why the RL agent's task is to learn a discounted return as opposed to learning, as opposed to focusing on maximizing the immediate reward. So consider that the vehicle has to reach its destination as soon as possible, right? So if we are using typical just an RL algorithm to guide the behavior of the vehicle, so in that particular case, whenever so that RL agent will try to move the vehicle at as high speed as possible, and will try to overtake any obstacle in its path as soon as it can, which may lead to some severe consequences. For example, in this particular case, there's an ambulance coming from the opposite direction, right? So if the RL agent focuses on only optimizing the immediate reward, then by taking an action, for example, let's suppose the actions are overtake, don't overtake. There are these two actions, right? So if the agent focuses only on the immediate reward, then if it overtakes the vehicle ahead of it, it will bring it closer to the goal, right? So in that sense, agent will feel okay that it is achieving its target, but it may fail to take some of the consequences of its action. For example, if an ambulance is coming from the opposite end, then the RL agent would fail to realize that maybe due to the bad representation or whatever reason, it may fail to realize that basically if it keeps on taking these greedy actions to actually maximize the immediate reward, it may lead to an accident, and that would just completely end the task, and the agent will never be able to reach its goal. And this is the reason why, rather than focusing on the immediate reward maximization, the goal of the RL agent is to maximize the discounted return, where the discounted return take both the immediate consequences in terms of RT plus 1 and the future consequences of an action in terms of the discounted sum of the future rewards. So the further the reward is in the future, the more discounted it is. For example, if the gamma is 0.5 and there's a reward signal at time step 100, then the discount factor for that reward signal would be 0.5 to the power 99, which is a very small value. This is the reason. I mean, this is an example to show like why we shouldn't focus on maximizing the immediate reward and focus more on maximizing the return. Before we begin our discussion of the algorithms, of the typical reinforcement learning algorithms, I just like to highlight the real world, like for example, in real world, ideally we would want to learn an optimal policy. That is a policy that, given a state, selects a sequence of actions that maximize the discounted return from that state. And in reinforcement learning, the RL algorithms try to learn this optimal policy. But in real world, typically we end up learning near optimal policy, which happens to be good enough for the practical applications. And an optimal policy can typically be learned only for tabular tasks. For example, the tasks where the states are discrete, actions are discrete, and as well as finite at the same time. So only for some limited tasks, the optimal policy can be learned. For most of the real world continuous robotics or autonomous driving tasks, it's very hard to even define what an optimal behavior should be, let alone learn a policy for a particular task. Furthermore, although it may look like that reinforcement learning is a totally, unsupervised in a sense that there is no reward, that there is no, label in terms of, data labeling that we have to do in supervised learning. But eventually the reward signal actually acts as a supervisor that decides what policies are good and what policies are bad. And this supervisor is often designed by a human, right? So it's a human that designs a reward function for a particular reinforcement learning task. And for most of the applications, it is very hard to comprehend as to what the reward function should look like. And due to these difficulties, I mean, it's often, we end up learning only the suboptimal policies. And again, even if we are able to learn the optimal policy, it's again going to be with respect to the reward function, which is again constructed by a human agent. So for simpler tasks, this may work, but for most of the complex real world robotics or autonomous driving tasks, it may not work in practice. So furthermore, if we talk in the context of autonomous driving, for most of the autonomous driving tasks, if we use reinforcement learning over there, we measure the goodness or the optimality of a policy by evaluating it against a human demonstrated sample or against a human demonstrated trajectory, whether either qualitatively or quantitatively, wherever it is feasible to actually compare the results quantitatively. For example, one of the very good examples of this is the overtaking problem, learning to overtake on typical two-lane roads in India. So this is a problem that I've been investigating for past 2.5 years now. So assume, for example, in foreign countries, I mean, the traffic laws are very structured. I mean, people are following traffic laws, the other obstacles and vehicles are following the traffic. Whereas in India, there's a lot of chaos on road, right? But still, Indian drivers are very good at overtaking on typical two-lane roads when there is a traffic coming from the opposite end. So when the opposite side traffic is active. Although you may argue that whether it is practical or not, but one thing is for sure that the problem is really, really complex. If you are able to develop the solutions and solve this problem, then the ideas and the solutions that are developed for solving such a complex problems, they can be used for solving many other similar problems of similar complexity, which may have a very immediate business use case. And furthermore, our goal in autonomous driving is to actually develop a technology that can deal with any kind of traffic and environmental scenario. And that's why this problem of overtaking on typical two-lane roads makes more sense to us as well. So in typical two-lane roads, the challenge is like, how do you design a reward function? For example, if you are talking about the recent successes of deep RL frameworks, like in the game of Go, in the game of chess, in playing Atari games, the reward function can still be engineered. For example, you can assign a reward of 1 if you play a game and win it, and you may assign a reward of -1 if you lose a game. But in tasks like overtaking, how do you design a reward function? If you think, okay, that I will just design a reward function that will give +1 reward if the overtaking is successful, and will give a reward of -1 if the overtaking is aborted. or if it leads to a collision, then this may lead to very suboptimal performances even in this simulator. Even if you have a perfect simulator to actually formulate this problem and try to solve as a deep reinforcement learning or reinforcement learning problem. So for many such tasks, like we try to learn the reward function directly from the interaction data that we get. But this is a separate discussion. I will discuss it towards the end of the presentation. Like this comes under the paradigm of inverse reinforcement learning. So in a nutshell, like what I want to summarize with this slide is that often in real world, the focus is more on learning near optimal policy with good enough practical performance. Furthermore, in real world, as I mentioned, like I mean, it's often hard to formulate a reward function for a particular reinforcement learning task, and often impossible for most of the autonomous driving tasks. In real world, for example, in autonomous driving in particular, policy is optimal. We define the goodness or the optimality of a policy either jointly or contextually or both. For example, consider another example. For example, the problem of navigating through a traffic intersection with no traffic light at peak traffic hour, right? So here, what is a good policy? What defines a good policy, right? So a simple reward function of navigating through an intersection of +1 and reward of -1 if it doesn't navigate through the intersection at each time step would make the agent go aggressive in the environment, right? So again, I mean, you can learn a policy if you could. You can learn an optimal policy that is very aggressive, but is aggressive policy really good? Or should you wait for the other obstacles to pass, get some space and then start, moving through an intersection? So, but in situations where the traffic, where there's no traffic light and the traffic is unmanaged, you may often just keep on waiting forever without even making a move if the policy is too passive. So what defines a good policy? What defines a good reward function, right? So here we have to take the context also into account. Like, is the context like, should we go aggressive or should we go passive? Or should we engineer a solution by combining several different, RL agents and learn a policy that basically automatically, maybe through some different function, maybe through a different algorithmic framework that decides whether we should go aggressive or passive, or maybe a big end-to-end deep RL agent with multiple collaborative RL agents making a decision whether to go aggressive or passive as well simultaneously, right? So it's very hard to design reward functions and hard to design the optimality of a policy, specifically if you're trying to solve the real world problems with single RL agents. Often in real world autonomous driving, we use multiple RL agents and we make them collaborate with each other. And in practice, when we use multiple RL agents to solve a problem, the focus is more on achieving the joint optimality as opposed to individual policy optimization for each of the RL agents. So here is an example that I wanted to present. So in this example, a vehicle is navigating through this environment, and the goal of the vehicle is to avoid any static or dynamic obstacle that may come in its path. And there's a motion planning and control framework that is using 5 different RL agents. So one of the RL agents is deep RL agent, and the other 4 RL agents are classical shallow RL agents. So these RL agents are collaborating with each other to decide, what the motion planner should do. So typical, for example, motion planners use the world representation to compute a trajectory for a vehicle. So they may be able to take the dynamics of other vehicles or obstacles into account and plan a safe trajectory. But usually the motion planners are not suited for the decision-making problems that have future consequences. So RL system is naturally suited for making decisions where the decisions have future consequences. Okay, I'm not able to pause this. So okay, I'll just like make it static. So basically, in this towards the end of the towards the end of this navigation task, suddenly a bike appears in front of our vehicle, right? So this was an unplanned scenario, and now, for example, if we had used a single RL agent, so you have to consider that this vehicle is navigating using only 2 cameras that are mounted on the front bumper. This vehicle has no lidar and no radar for computing various environment parameters. On top of that, the vehicle is navigating through a very tight region. So towards the end, a bike suddenly appears, and if the and the task ahead of the RL agents is to decide whether they should tell the motion control framework to apply the brakes or let the vehicle navigate through this intersection. Through that region. So interestingly, the RL agents jointly decided not to apply brakes and let the vehicle pass. So when the vehicle passes the two bikes, there's just 15-centimeter gaps on either side. Now assume if we had used a single RL agent to actually control the to actually govern the motion control behavior of the vehicle. So in that single RL agent, based on my experience, I'm pretty sure that the RL agent would have commanded the motion control and trajectory planning framework to apply the brakes or to significantly slow down, right? But in a collaborative fashion, and perhaps we would have thought that that policy is optimal, because we see, okay, that the environment is fairly the environment is tight. I mean, there is the biker can take some stochastic actions. It may directly come in the path of the vehicle, so it would make sense for the R agent to command the vehicle to stop, right? And we would have thought that that is an optimal behavior, right? But by using collaborative multiple RL agents, again, the question is, okay, is it possible to navigate through such regions without stopping? Because we as humans in India do this on a regular basis, almost every day. We drive our vehicle through very tight regions with moving traffic, right? So the question here is, can a collaborative RL agent allow a vehicle to pass through such tight regions in where the other obstacles are dynamic, and keep the vehicle, and the environment safe as well at the same time? So if we had used a single RL agent, probably would have never, found, okay, that this kind of behavior is even possible, that we could allow a vehicle to navigate through such a tight environment. But by using multiple collaborative R agents, we were able to not just make this happen, but we actually found, okay, that there is a better behavior. Which which may result into overall better autonomous driving abilities, and can deal with situations where a single RL agent may not have been able to deal with. So this is why the slide is a bit philosophical in a sense, basically, that I mentioned that basically the optimality of the goodness depends on the contextually, on the context, as well as in the, for example, if we are using multiple collaborative agents, then the focus is on joint optimality. So again, like, we didn't try to optimize each of the RL agents in a sense that we didn't focus on the individual policy optimization, but we focused during training on the individual, on the collaborative optimization of the decision making process. So those RL agents were computing several different parameters in the environment that eventually allow vehicle environment to remain safe. And collaboratively, they were able to allow a vehicle to pass through such a region. So in practice, typically, if you're using a single RL agent setting, typically we end up learning near optimal or suboptimal policy. But in the context of deep RL, that suboptimal policy happens to be good enough practically. And for most of the complex applications, typically we use multiple collaborative RL agent rather than using single RL agent to make a decision. So having discussed, the typical RL framework, like what is the interaction model and what are the typical use cases of reinforcement learning, we'll now, briefly sort of cover the mathematical formulations, and then I'll cover some of the algorithms, to solve the reinforcement learning problem. So first of all, I'll define I'll define the Markov property. So for this, I will define two terms. One is the transition probability, and the other is history. So the transition probability, denoted as P S prime given S comma A, is a probability of an agent transitioning to a state S prime, given that it takes action A in a state S. So it is denoted by P of S prime given S comma A. And the history is basically a set of a sequence of observations and the actions that the agent took until it arrived in state ST and took action AT. So this is the history. It's a sequence of observation from the beginning until the state ST and up to the action 80% that was taken by the origin. So now, if a model satisfies the Markov property, or if the state representation of the environment of the world is Markov, then the transition dynamics simplifies. For example, if the state satisfies the Markov property, then the probability of transitioning to the next state as t plus 1 given the current state and the action taken in that state is independent of the history. So if the world or the state representation satisfies the Markov property, what essentially it means is that the RL agent can base its decisions only on the current state. So what matters is the current state observation, and now and not how that observation was arrived at. So it doesn't matter how you arrived at state. All that matters is what state you are in, and this significantly simplifies the decision making process, because the RL agent doesn't have to worry about the history as to how it arrived in a particular state. It can just base his decisions on the current state, and history need not be kept for any of the decision making purposes. So if a world or the state representation satisfies the Markov property, uh, then the then the task basically becomes a MDP, or a Markov decision process. Sometimes even the non-Markovian even the non-Markovian RL tasks are formulated as a MDP. So MDP in a nutshell is basically a set of all states, a set of all actions, the transition probabilities, P S prime given S comma A. Later in the talk I've also used this representation P as a function of S prime to mean the same thing, and similarly there's a reward function and a discount factor. So an MDP is basically is defined by these five variables: the state space, the action space, the transition dynamics, or the transition probabilities, the reward function as to how the rewards are generated in the environment, and the discount factor gamma. And again, just like in regular RL that we have discussed so far, that the goal of the agent is to maximize the discounted return. Here also, the goal of the RL agent is again take actions and maximize the discounted return. So now, to facilitate our further discussion, I will formally define the policy and the value function for a policy under an MDP. So a policy can both be stochastic as well as deterministic. So a policy in a nutshell just maps states to actions. So if the policy is a deterministic policy, then it will deterministically map the states to actions. If the policy is stochastic, we'll represent it as pi of s comma a, then basically it provides us the probability of taking action A in a state S. So this is a distinction between the stochastic and the deterministic policy. Similarly, we can now define the value function. Recall earlier that we discussed the value function is a function of a policy. So the value function for a policy pi under an MDP is defined as, so there are two different kinds of value functions. One is a state value function that stores the state values, and the other is a state action value function that stores the state action values. So the value function for a state S under a policy pi is the expected value of the discounted return given the state S when all the actions in state S and all the subsequent when the action state S and all the subsequent actions are followed by the policy pi. And again, here we can use the definition of the discounted return to write the state value function again as the expected value of the discounted return, given that the current state ST is state S, and the actions the action state S and all the subsequent actions are governed by the policy pi. Similarly, state action value function is defined as the expected discounted return from that state, given that we take action A in state S, but all these subsequent actions are followed by policy pi. So again, we're using the definition of return. We can simplify it as Q. The value of the state action pair under a policy pi is the expected return following state S, given that we take action A in a state S, but subsequently we follow policy pi to take all the further actions. So this is the formal definition of the state value function and the state action value function. So having defined this, I'll just define two more equations, the Bellman equations. So after some few mathematical steps, so these are trivial mathematical steps, we can easily show that the value function for a policy pi under value function for a state under policy pi satisfies this recursive equation. That is, the value of state S is the expected value of the immediate reward plus the discounted expected value of the next state under a policy pi. Similarly, we can define the, we can again using some trivial mathematical steps, maybe 4 or 5 trivial mathematical steps, we can easily show that the state action value function satisfies this equation, where what this equation essentially means is that the state action, the value of the state action pair under policy pi is the expected immediate reward that is obtained by following action A in a state S, plus the discounted expected value of the next state, right? So these equations are known as the Bellman equations. Likewise, there are Bellman optimality equations as well, but we don't need it for the discussion. When it matters, I will present the Bellman optimality equation as well. So these are the Bellman equations for the value functions, for the state value function and the state action value function under a policy, under an MDP for a policy pi. So having learned what a policy is, what value functions are, what transition probabilities are, and what reward functions are, one of the natural questions to ask is that, is there a method that, given the perfect world information, for example, if you perfectly know the transition dynamics, if you perfectly know the reward function, if you perfectly and also the states and the actions are discrete, as well as the states and action sets are finite, are there methods that can allow us to learn the value function and policy? So the answer is yes. There are some class of methods known as dynamic programming methods that actually use this perfect information to actually learn the value function for a policy pi, and these are iterative methods. So basically, they learn. They start with a random policy. For example, where there are two methods. One is the policy iteration, and the other is the value iteration. So given the perfect world model, there's a transition probabilities and the reward function. And if the states and actions are discrete, then we use the dynamic programming methods to compute the policies and the value function for a given reinforcement learning task. So this is a brief summary of policy iteration. So since these algorithms are very limited in scope, since there are very strong assumptions, I have not gone into the detailed mathematics of these algorithms. So just like, but for the sake of simplifying our future discussion, I'll just sort of briefly summarize what policy iteration and value iteration is. So policy iteration has two components: the policy evaluation step and the policy improvement step. So the policy iteration algorithm starts with a random policy. So the evaluation step uses the Bellman equation that we have described over here to actually iteratively compute the value function for this policy. So once this value function is computed for this policy in the evaluation step, the next step is to improve the policy using the learned value function. And the way it happens is that the policy is set to be a greedy policy with respect to the state action value function. That is, the policy is deterministically set to take actions that lead to the maximum state action value. And this process iterates. So we have a policy pi one, then we evaluate in the evaluation step, we again compute the new value function, and then we improve the policy. And iteratively, the policy iteration can be shown to converge to the optimal policy and the optimal value function. Similarly, there's another algorithm known as value iteration. So in policy iteration, I mean, we have this evaluation and iteration step. That is, we have to first compute the value function and then compute a policy and then recompute the value function, which is very data, which is very sort of exhaustive amount of computations. So we have another algorithm known as value iteration, which doesn't have this improvement step. So it iteratively, uses the Bellman equation to iteratively update the value of each of the state at every time step. So basically, the value at the next step is is basically this expression, and this equation is recalled iteratively, and it can be shown that basically the sequence vk converges to the optimal value functions. That is the value function corresponding to the optimal policy for the task. And then once we have learned the optimal value function, we can again compute a policy that is greedy with respect to the state action value, optimal state action value function, by setting the policy to deterministically take action that results into the maximum optimal state action value for all the states. So these are dynamic programming methods which make use of the perfect information about the world. So they need the entire world model, which is the transition probabilities and the reward function. And also there's a significant assumption that the states and actions are finite, and the states and action sets, the states and actions are discrete, and the states and action sets are finite. So due to these assumptions, these dynamic programming methods are very limited in scope, and such methods work only for tabular toy world problems. I mean, for example, the grid world problem that you typically see in reinforcement learning book. So basically we will restrict our discussion into dynamic programming. But the previous equations basically will help build a mathematical foundation for understanding the other reinforcement learning algorithms. So once we understand the shortcomings of the dynamic programming methods that require the perfect world information, we can appreciate the other methods that actually don't require such information. So it helps in building the mathematical foundation for reinforcement learning. So now we will begin our discussion with the real world, the algorithms that are used for solving the real world control problems. So there are several, depending on what algorithm we are using, there are different divisions of the reinforcement learning algorithm. Broadly, we can categorize the reinforcement learning algorithms into two categories: the model-based methods and the model-free methods. So the distinction between these two is that the model-based methods either require a model to be given to them, or they learn the model from the interaction data of the agent environment interaction. So either the model is learned or the model is given beforehand. And the model-based methods may use this model for either fine-tuning the decision-making process, or for generating the artificial data samples to for the RL task. For example, because generating, for example, for most complex, real-world applications, I mean, usually, I mean, we require a simulator, right, to generate the amount of data that is required to train the reinforcement learning method. So if we are short on data, then model-based methods can actually use the model to generate the artificial data to facilitate the policy or the value function learning. But there are other problems associated with this artificial data, which we'll be covering in the later slides. The second approach is the model-free approach. So unlike model-based methods, model-free methods do not require a model to be given beforehand, and they also do not try to learn any model from any data whatsoever. So these are the algorithms that directly try to learn the control policy either explicitly or implicitly via value function. So they will either learn a control policy or learn a value function and learn a policy from this value function. Furthermore, there are three other divisions of the RL algorithms. So these are value-based methods, actor-critic methods, and policy-grade methods. So the value-based methods are the ones that focus on learning the value functions. Is either state value function or the state action value function. Mostly it is the state action value function. And the policy is derived from the computed value function. For example, let's suppose if we have have a Q value function, that is the state action value function. And if you are in a particular state S, and if you have to decide what action, let's suppose there are two different actions, right? And you have to decide which action to take. So we can just query the Q function. So we can compute Q of S comma A1 and Q of S comma A2 to know which action to pick, right? So we can query Q function to know which action will lead to a better discounted return. Then there are policy gradient methods. So these methods do not learn a value function, they directly learn a policy. So directly a policy is learned or optimized in the policy gradient methods. Then there are actor critic methods which learn both the value function as well as the policy, and as a result they combine the merits of both the value based as well as the policy gradient methods. So this is a broad classification of various reinforcement learning algorithms that are used in practice. So here we'll just like briefly go into the merits and demerits of value based as well as and the policy optimization method. So the value based methods, one of the demerits of the value based method is that they require actions to be discrete, and also they require action set to be finite. So if the actions are discrete, but the action set is practically infinite, then basically it's just a problem for value-based methods. They do not scale well, and they are not designed to inherently work with a continuous action. And most of the real-world robotic and autonomous driving control tasks are continuous in nature. For example, the actions are continuous. For example, let's suppose if the goal is to learn the steering control end-to-end from the raw sensory data, then if we are using value-based methods, then we have to discretize the steering position. And then the next question is, okay, what level of discretization should we use? Should we use 1 degree discretization? Should we use 2 degree? Should we use 3 degree to actually discretize the steering position? So this is a problem with value-based methods, and that's why they are limited in scope. But nonetheless, they are heavily used in practice for control applications, where the actions are discrete and the action set is small. Policy gradient methods are inherently designed to work with the continuous actions. So they don't suffer from the same problem that value-based methods suffer from. And that is why they are better suited for real-world control applications where the actions are continuous. And to give you an example, for example, if any of you have worked in robotics, and if any of you happen to work in motion planning and motion control and trajectory tracking, then you know that once the trajectory is planned for a robotic system, if the robot is navigating at low speed, we can come up with trajectory tracking algorithm that can track the trajectory fairly well. But the problem becomes severe when the robot or the vehicle is navigating at very high speed. So currently we are working on designing end-to-end deep reinforcement learning against based on policy gradient approaches. So the deep policy gradient methods to actually learn both the hyperparameters as well as learn the controllers end-to-end for the purpose of trajectory tracking at very high speed. So this is the real world, significance of policy gradient methods. Then there are actor-critic methods I mentioned earlier. They combine the merits of both the value-based methods as well as the policy gradient methods. And one of the advantages of actor-critic methods is that they naturally scale. They are naturally designed for the continuous action space. So although the value-based methods are not designed for the continuous actions, but the policy gradients are. But if you use actor-critic, then we have an advantage of both having a value function as well as a policy, as well as a merit of a policy gradient method where we directly learn a policy, and we share the advantages in a sense that we can model the continuous actions in the actor-critic framework. Again, like briefly comparing the model-based and model-free approaches. Model again is model is a function that predicts the state, transitions, and the reward function. So such models basically, as you can deduce, I mean, such models are not readily available in the world except for few real-world tasks. For example, if you are designing end-to-end deep power system for the game of Go or for the game of chess, then you can know deterministically the outcome of every action that you pick. For example, in chess, there are only so many moves at any given time step. And when you pick a move, you can deterministically know how the state of the environment or the state of the chessboard is going to change. But this is usually not the case when the actions or the or the states are continuous. So if any of them happen to be continuous, then basically it's very hard, to learn this model. Furthermore, in model-based approach, as I discussed earlier, either the model is given or they try to learn the model from the interaction data. And if they try to, and if they learn the model directly from the interaction data, then there can be some biases in that model, which can further lead to suboptimal performance as compared to having no model at all. But one of the merits of these approaches is that if they work really, really well. And the AlphaZero, I think you all would have heard about the AlphaZero, is a very good example of model-based deep end-to-end RL. For most of the real world control application, specifically in the context of robotics or autonomous driving, we focus more on the model-free methods, although we can use model-based methods. We are investigating that, but the scope is very, very limited because there are so many limitations of, it can only be used. I mean, you have to discretize a state, you have to discretize the actions to be able to use the typical model-based approaches, specifically when the problem is as complex as one of the tasks of autonomous driving. So model-free methods do not require a model to be given. They don't try to learn a model. They directly learn a control policy, either implicitly via value function or explicitly as in policy gradient methods. These are better suited for the real-world control problems, as I already mentioned. And traditionally, I mean, the model-free methods are more heavily used as compared to model-based methods. And these are also more tested as compared to the model-based reinforcement learning. So now for some portion of the discussion, we will entirely focus our attention on the value-based model-free methods. So there are two classes of algorithms. One is the Monte Carlo methods and the other is temporal difference learning methods. So Monte Carlo methods are value-based methods. That is, they try to learn the value function. Again, they try to learn the value function via the natural interaction data that we discussed earlier. But one of the limitations of the Monte Carlo methods is that they require a terminal state. For example, what a terminal state is. So a terminal state is a state where a particular task ends. For example, in the game of chess, if you win, the task ends. So winning is basically whatever the state is, it's a terminal state, right? For example, let's suppose if you're solving grid world problem, like many of the problems are concerned in the reinforcement domain. So if arriving at a particular grid cell, achieves the goal, then that's basically a terminal state. Basically. So Monte Carlo methods are suited for tasks where there's a concept of terminal state, whereas most of the real world control tasks do not have any terminal state. For example, consider autonomous driving. It's just a continuing problem. There's no end. I mean, to the only when the driving ends, then they basically the origin stop working. But from the RL agent's point of view, the task is continuing rather than having a terminal state, or rather being an episodic task. So the tasks that have a terminal state, we call them episodic tasks, and Monte Carlo methods are more suited for episodic tasks. And even if they learn incrementally, the incremental learning happens only on episode by episode basis, and you have to wait until an episode ends to actually update the value function. And that's the limitation of the Monte Carlo methods. And and this is a problem that the temporal difference learning methods get rid of. So the temporal difference learning methods, or the TD learning algorithms, in these algorithms, learning happen at every time step of the agent environment interaction. So in a sense, learning is more natural, and there are two popular algorithms in temporal difference learning. These are SARSA and Q learning. So SARSA is on policy and Q learning is off policy. What on policy means is that it will learn a value function for a policy that is being used to collect the data. Whereas in Q learning, no matter what policy you use to collect the data, in the agent environment interaction model we discussed, the agent takes action according to some behavior policy. So no matter what behavior policy you're using to collect the data, the algorithm will always try to learn or approximate the optimal value function. That is the value function associated with the optimal policy for the task. So in a sense, SARSA can only learn the value for the policy that is being used to collect the data, whereas Q learning can use any policy for learning the optimal value function. And that is why these are more suitable for real world problems. So here we will briefly describe both the algorithm SARSA and Q-learning. So recall our earlier interaction model of the agent environment interaction. So at every time step we discuss the agent is in state S, it takes an action AT, gets a reward RT plus 1, makes a transition to ST plus 1, and gets a new reward. It takes another action AT plus 1, and the process continues from there. So the SARSA exactly uses the current state, the current action, the reward signal that we obtain as a result of taking action A in state S. It takes the next state and next action into account to make an update to the value function, right? So the value function, and that is why SARSA derived its name. I mean, this is a reason why it is called SARSA, because it uses the state, current action, the reward, and the next state action pair. So this is the update rule for updating the value function in case we are using SARSA. So we can start with an arbitrary value function and make it, and iteratively we sort of iteratively get the data from the agent environment interaction model and use that data at in this update rule to actually iteratively compute the value for the behavior policy. This is a policy that is being used to collect the data. So this term, so this update equation here, the updated Q value takes a current Q value plus alpha, where alpha is a learning rate, plus the immediate next reward, plus the gamma times the value of the next state action pair minus the current state action value. So this term in this square bracket is known as the TD error. So recall earlier the Bellman equation. The value, the state action value under a policy pi is the expected immediate reward plus the expected discounted value of the next state under a policy pi, right? So we use the Bellman equation basically to actually come up with the update rule for both the Q learning and the SARSA algorithm. So here this term is known as a temporal difference error, that is the TD error. That is the ideally the value of the current state action pair should be the reward signal plus the discounted value of the next state action pair. But since we are learning the Q value iteratively, there's going to be some difference. And this difference generates an error. We call it TD error. And this TD error is used to actually update the Q values iteratively. So since this is an off policy, it means that it will learn the value function associated with the policy that we are using to collect the data. And that is why in practice, we use what we call epsilon greedy policy. That is, the policy will always take the action, will almost always take the action that results in the highest Q value, but with some small probability epsilon, it will take an action randomly. So this is what epsilon greedy policy is. And gradually, as the learning converges, we can decrease the value of epsilon. So for typical tasks, we select value of epsilon to be 0.05, and as our training converges, we asymptotically reduce the value of epsilon. The next is Q learning. So again, like Q learning is again iterative. So it incrementally updates the value function, the state action value function. And the difference between SARSA and Q learning, there are two differences. One, SARSA uses the current state action pair and the next state action pair in the reward to make an update to the value function. Whereas the Q learning only uses the current state action pair, the reward, and the next state. It doesn't use the next action. It doesn't use the next action to actually update the value function. So also here we use the discounted value of the next state action pair, whereas here we use the discounted value of the best next state action pair, right? So the max over here selects the value among all the action. It picks a value of a state action pair that results in the highest Q value. So the TD error. So again, this term in bracket is called the TD error. And again, here the target for the optimal policy, the value of the state action pair should have been the reward plus the discounted value of the next state action, next best state action pair. But since we are computing this iteratively, there's going to be some difference, and this difference generates a TD error. We call it delta T, and this is used to actually iteratively update the Q value. So this is exactly, for example, if you were to implement SARSA or Q learning in your computer, this is the only update equation that you will have to actually implement in your computer to be able to learn a value function, where alpha is a learning rate. Just like in machine learning, there's a learning rate. For example, in gradient descent, similarly here, the alpha is a learning rate. And there are various heuristics to select the value of alpha. Again, the Q learning is off policy because of this max operation over here. So basically, it learns it approximates the optimal state action value function that corresponds to the optimal policy for the task. And it is one of the most important classical reinforcement learning algorithm. Most of the deep RL methods are based on Q learning. So basically, in the interest of time, I will just I'll not go through all the equations. I'll just we just have 20 more minutes left. So in the interest of time, I'll just briefly summarize the difference between Q learning and the double Q learning. So basically, you notice that basically here there is if you observe the TD error, then it's RT plus 1 plus gamma times max over A Q of ST plus 1 comma sorry, here it should have been A. There's a small typo. It should have been A over here. So basically, if you look at the TD error over here, there's an immediate next reward plus gamma times the best next state action value. So this is a target for Q learning, and there's a TD error. So if we look at this term, we can expand it, and this term can be rewritten as Q of ST plus 1 plus R max over A of Q ST plus 1 comma A, right? So in a sense, this is using the same Q. So remember that the agent is iteratively learning, the RL algorithm is iteratively learning the value function. And then it is using the same value function to both evaluate as well as to select an action. So this creates a problem known as the overestimation bias. So it is more likely to select the overestimated values and less likely to select the underestimated values, and that creates a bias. So this is a problem that is being resolved by an algorithm known as double Q learning. So in double Q learning, rather than having a single Q estimate, we maintain two different action value functions, Q1 and Q2. For Q1, we use Q2 for evaluation and Q1 for action selection. And for Q2, we use Q1 for evaluation and Q2 for action selection. In practice, we actually at each step we randomly pick one of those and we update one of those. And why this algorithm, why this double Q learning is important is that the deep variant of double Q learning, which is DDQN, outperformed in all the Atari games the deep variant of Q learning, which is the DQN. So that is why I wanted to mention this algorithm. Otherwise, this algorithm serves no other purpose. So until now, with this slide, I will summarize the classical RL and focus attention to the deep RL only. So observe that in all our discussion, in all our equations, wherever we have used equations, we have indexed the Q values directly with the states and actions. And this is feasible only when the states and actions are discrete, or when the states and actions are finite. So for example, if the states and actions are discrete but practically infinite, it would be very hard to store such a table in your computer memory, right? So also, if the states are continuous, then we cannot use this kind of indexing, right? So this is where for the continuous, so remember that the value function based methods cannot work with continuous actions. They can only work with continuous states. So in case where the states are continuous, it would be it would be impossible to to use that indexing, and to even if it discretize, it would be practically infinite states, and it would be very hard to store such table in a computer memory. So for such problems, we use linear approximation of the value function. No, we call it linear value function approximation, where the value functions are approximated by a feature representation of the state variable, right? For example, let's suppose if you have a particular task where the state has two continuous parameters. So the state is defined by two continuous parameters, and those parameters are continuous. So it would be impossible to use the previous formulations that we have discussed. So we'll just construct a feature representation over those state parameters, and we linearly approximate the value function as some feature vector of the state times some learnable parameter W. And similarly, for the Q values, we have some feature vector of the state action pair times some learnable parameter. So the temporal difference learning methods with the linear function approximation update the learnable parameters W. So the update equation looks something like this: that the Wt plus 1 takes the value Wt plus alpha times some correction times phi, the feature vector of state action pair, where the correction term is a TD error. So we can use the standard definition of TD error for Q learning and SARSA, and we get the update equations for the Q learning as well as the SARSA. So here again, we have used a standard definition of the Q function over here, and here also we have used a standard definition of the Q function from the linear value function approximation. So I will skip. So I wanted to summarize the application of classical RL approaches, but in the interest of time, I will just skip this slide for now. So I'll just focus on this slide. For example, if you observe, if you have seen our demo, for example, there are several demos on our website. You notice that in 2017, our staging was, in all the demos, our staging was very jerky, whereas in 2018, all our demos, the staging was very smooth. And basically, the mechanical disturbance was because we were using a very old vehicle. There's a significant lag. For example, if you rotate the steering, the tire will be rotated after some time. So there are several mechanical issues. And also we have, retrofitted with a custom design electromechanical system, which is not of industrial grade. So this resulted in significant, disturbance in the steering. So this is where I use classical, RL Q learning to be specific. With this state, so there's a lot of there's a lot of reward engineering that actually happened to make this happen, and a lot of feature engineering in terms of the state representation that actually went into this task. But through Q learning, we were able to significantly smooth our steering. And when this demo was done, we were still fine-tuning some of the parameters of this end-to-end controller for the steering. And after a month of training, we were able to finally obtain a very smooth controller with very few jerks. I mean, in case if they happened, they were very small as well. So you can see some of the demos on our website from 2018 to see how we sort of obtained this smoothing. So this is a classical example of classical RL being used in real world for solving a real world control application. So now for the rest of the discussion, I want to focus on the deep reinforcement learning methods. So deep reinforcement learning is basically the classical RL methods plus the neural network. Recall our discussion in the machine learning and in the supervised machine learning classical supervised learning and the deep supervised learning. So there, the deep learning helped us in automatically learning a good representation, as well as a function for mapping the input features to their target values. So the same thing happens in deep reinforcement learning. So recall, I mean, for example, consider this example on the left. Let's suppose our goal is to end-to-end control the steering of the vehicle, right? So now the question is, how do we formulate the state? What parameters should we select to represent the state of the world? Should we use lane markers, positions? If we use them, then to what extent, up to what depth should we use them? Should we use the road boundary information? Should we discretize them? Should we use the velocity information of other vehicles? Should we take the ego motion into account and represent that as a big state vector? And then on top of that, since all these parameters are continuous, we'll have to eventually use value function approximation. So again, we'll have to construct another feature function on top of the state parameters. So there's a lot of engineering that happens, and there's a reason why classical RL methods do not scale well for the real world control applications, because it is very hard to engineer a good state, a good set of state parameters that capture the complexity of the world dynamics. And the linear value function and the linear value function approximation on top requires us to design a feature function, and furthermore, the dependency over there is linear. For example, in linear value function approximation, the value function is linear in terms of the learnable parameter. So this further, adds to the difficulty in capturing the complex dynamics of the world. So this is the problem that deep RL methods mitigate. So in a nutshell, this is classical RL, where we have an input image, we will extract some state parameters, and then we will construct a feature representation, then we'll learn a policy and then from that policy or value will select an action. In deep reinforcement learning, we can directly feed the raw sensory data to a deep RL system, and it would be able to both construct inherently as a part of the parameters of a neural network, construct a good representation that captures the complexity of the dynamics of the world, as well as learn the value function or the policy again as a part of the parameters of a deep neural network. So this is what, in a nutshell, deep reinforcement learning is. It is classical RL algorithms plus a big neural network in the middle. So one of the examples of deep reinforcement learning is the DQN method, which is a deep variant of Q learning known as deep Q networks. So the advantage of DQN is that it can learn from the raw sensory data from a robotic system or from an environment or from an autonomous driving vehicles sensor. So this raw sensory data, for example, we can feed the raw images, raw lidar scan to the deep RL system, and it would be able to automatically construct a good state representation, as well as a good a good representation that captures the world's dynamics, as well as inherently learn the Q values. So this is something that is impossible to be accomplished from classical RL methods. For example, one of the problems that I've been investigating over past 1 year is what I call off-shift policy. That is, for example, if you're driving a vehicle on a tight road, and the road is narrow, that it cannot accompany two vehicles at the same time, right? For example, in case a truck comes to a picture, then you have to go off roads. So the question here is, at what point do you shift off roads? If you shift, how much do you shift? And if you really make a shift, what are the commands additionally that you generate for a motion planner, so that it can generate a trajectory for the high level decisions that are made by an RL agent? So these are some of the questions that are really hard to answer from a classical RL point of view. Why? Because, for example, in classical RL, we again would run into same problem, like what state parameter should we use? Should we use lane markers, road boundaries? Should we use bounding boxes, or should we use mask of the obstacles? Should we compute the velocity of other vehicles and the ego motion of the vehicle and store that state representation and build a feature function on top of that? So this is a very hard, problem statement. I mean, to construct such a representation that would be able to comprehend the complexity of the world dynamics, it's almost impossible to engineer such a representation. But the deep RL methods can directly take the raw images as an input and can directly learn an off-shift policy. Although this is not, to let you know, this is a very bad approach to go with. For example, if you directly try to learn from the images, because what happens in autonomous driving vehicle, there are all algorithms that are already operating. So in an autonomous driving vehicle, the perception stack will already have algorithms that will compute the road information, the lane information, the obstacles, their trajectories, their velocities, the ego motion, and many other parameters of the environment, right? And on top of that, if you design for a simple task like off shift, for example, not simple, I mean for a small task of a broad, set of from a broad set of autonomous driving problems, if you devote an entire end-to-end deep RL that directly takes the input, the raw sensory data, then a lot of repetitive computations would be performed. For example, you can prove it. For example, take a vehicle, mount few cameras on it, drive the vehicle end to end, and try to don't go into deep RL, just go with deep end-to-end deep learning, end-to-end deep supervised learning, right? Where your goal is to learn the steering commands. So if you train with lots and lots of data, and if you try to visualize the feature maps of a convolutional neural network, for example, what you'd find is that those convolutional networks would inherently learn the road bounds. They would inherently learn the lane information. They would inherently learning the obstacle information, right? They may not be explicitly be able to represent the boundaries as it is, but there are several feature maps that will be learning many of these parameters, and a combination of that combined with a fully connected layer will help you in controlling the end-to-end steering of a vehicle and design an autonomous vehicle as well. So you see, I mean, if we go with the end-to-end deep RL approach where we learn directly from the raw pixels, there will be a lot of repetitive and waste of computation. Furthermore, there will be other RL tasks as well. For example, offshoot is one policy, overtaking is one policy. Motion primitives is another policy. So should we devote an R system to each of these problems? That would be very bad approach. So typically we are investigating three ideas. From research point of view, yes, we are investigating the end-to-end learning from directly from pixels. But from practical point of view, we are using what we call, for example, in autonomous driving, you map you build a world representation and you map the representation on top of local 2D occupancy grid. You can also design a local high dimension lattice, which can be dynamic in nature as well. So it can compute all the environment parameters and store in the form of local high dimension lattice. It's your choice whether to make it static or dynamic. But we are investigating, can we feed that entire lattice, which already has information encoded from various algorithms that are already running in the perception stack. So there would be, thousands and thousands of nodes, if not millions of nodes in the local high dimension lattice. So we are investigating, can we directly feed that lattice to an RL agent? And in a sense, it would be getting much more structured information and won't be doing the repetitive computation, and that would be a waste of computation sort of as it is. So there are some real world challenges as well when you try to solve every problem directly from the pixels. Although so this example is specifically from from an autonomous driving point of view. There have been tremendous successful applications. So I will come back to these equations. I mean, again, like, these equations are simple, but in the interest of time I will have to skip this equation. So these are the equations of DQN. Again, like, for example, we use the Bellman optimality equation to actually compute the target in Q-learning, and for example, recall that this was the TD error in Q-learning, and this is actually the loss function that we use in DQN. So basically, the ideas, the regular ideas from the Q-learning actually directly translate to the DQN. And these equations, show the equivalence. The only thing that changes is a neural network that actually approximates the Q value and learn end-to-end representation as a result. So I'll just skip these equations. In practice, I'll just mention. In Q learning, we use the same Q value for evaluation and action selection. In DQN, since we are using a deep neural network, if we go with a single network, then the target for the current network would be non-stationary, because there is a lot of fluctuation that would be happening if we use the same network over here. So what happens in practice is that we maintain two different networks. One network we denote by Q theta minus, where theta minus are parameters of one of the networks and theta is a parameter of another network. So once in a while, the theta minus are updated less often. So once in a while, we just copy the theta into the theta minus parameter. So this helps add stationarity in terms of the target for the Q for the deep neural network. Or target for the estimate of the state action value function. So this adds stability in the training, and there have been tremendous successful examples of DQN and double DQN in practice. For example, the Atari games by DeepMind. They learn directly the control policy from the raw pixels of these games. So these images were fed to the deep RL system as raw input, and the RL agent, the DQN and the DQN learned a control policy directly from the raw images, and they outperformed any human benchmark that existed. And why earlier I mentioned that, basically I mentioned double Q learning for purpose. So the reason for earlier stating, mentioning about double Q learning is the fact that double DQN, a variant of deep variant of double Q learning, outperformed the DQN or deep variant of Q learning in all the Atari games, and basically double DQN works better in practice as compared to DQN. So this is an example of deep reinforcement learning, the value-based method applied directly to learn a value function directly from the raw sensory data. So so during inference, you supply this image again, and the neural network will provide the Q value of all the possible actions. So if there are n possible action, you have n possible Q values, and then you select an action that has a maximum Q value. So again, just like in typical value-based methods, which are not designed inherently to deal with the continuous actions, similar is the case in the deep Q methods. which are again value-based methods, and that is why they cannot model the continuous actions, and that's why their scope is limited when we talk about the real-world control problems, especially in the context of robotics or autonomous driving. So again, if we briefly discuss this problem, so consider again that off-shift policy task, where our goal is to decide how much to shift, when to shift, and how to shift, and if we shift, should we generate some motion commands, some high-level motion commands for the inherent motion planner or the inherent motion control framework. So, for example, if we try to solve it with regular DQN or double DQN, then we'll have to ask certain questions. Okay, there would be yes or no type of questions. I mean, there would be the amount of shift will have to be discretized, and that will add to the suboptimality to a task that requires very high precision. For example, if you're navigating at low speed, this is fine, but the moment the vehicle attains higher and higher speeds, this discretization can create some severe consequences, right? And then basically, like, what new guidelines to be generated by the deep system for the inherent motion planner that will compute the trajectory for the high-level motion commands. So this is a very tough problem, to solve with regular deep Q methods, and this is where we make use of the deep policy gradient based methods, which directly work with continuous action. So we won't have to discretize the action space over there. We won't have to discretize the amount of shift. We can also end-to-end learn the velocity, I mean decrement. We can either state it as a quotient that should be increased or decreased, or we can directly learn a continuous value for the velocities when we are making a shift. So these are the some of the questions that we are currently investigating as a part of our research to solve this off-shift policy problem. I will just there are 3 more slides. I mean, I think if I'm allowed to, I will just add 3 more slides to end the discussion. So as I mentioned, I mean, I'll just briefly summarize the deep policy gradient methods. So as we know that deep Q methods suffer from the suffer when we have continuous actions, or when the number of actions is practically infinite. So in those cases, we make use of policy gradients, which are inherently designed for the continuous actions. And basically, this is what there's a difference between policy and the value-based methods. So in value-based methods, we learn a value function, and then we learn a policy from that value function. In policy gradient methods, we directly learn or optimize or compute a policy instead of learning this middle value function. And basically, this is inherently designed to deal with the continuous actions. And although the classical policy gradients have some convergence issues, and they cannot deal with the level of complexity that is present in the real-world control applications, but the deep variants of the policy gradients, they work well for the real-world control problems, because of the deep neural network that can comprehend the complexity of the world in which the RL agent is operating. So this is what, in a nutshell, deep policy gradient methods look like. So again, just like in traditional RL interaction model, basically at each time step given a state, we select an action, or we take the highest probable action if the policy is stochastic. We select the most probable action if the policy is stochastic. We then observe a reward signal, and basically using that reward signal, we update the parameters of a deep neural network, just like it happens in DQN. The same is the case in deep policy gradient methods. And here's a representation, a crude representation of what a typical end-to-end deep policy gradient method would look like. So we have an observations from the environment. We have a big neural network that directly learns a good representation that can comprehend the complexity of the dynamics of the world, as well as directly learn a policy as a part of the parameters of the deep neural network. So the deep neural networks directly encode a policy, and the network can directly output the actions, as well as can output the probabilities of actions to take, depending on whether we are using a stochastic policy or deterministic policy. So here's one famous algorithm, deep deterministic policy gradient. It's an instance of actor-critic method. For example, it's a bridge between the DQN and the policy gradient. For example, the DQN cannot inherently work with continuous actions, whereas a deep deterministic policy gradient can work with continuous action. It has an advantage of both the value based and the policy gradient based methods. So since it's an activity framework, it both learns a policy in an end-to-end fashion. So since it's a deep RL method, it learns a policy end-to-end via neural network. Furthermore, it has two parts: the actor and critic. So the critic is a value function, and the actor is the policy. And typically, the critic is again represented by a neural network, and the critic learns the value function of that deterministic policy. So unlike DQN, it's able to handle the continuous action space, and essentially DDPG can be thought of as as an extension of DQN for continuous actions. So this ends the talk on reinforcement learning. I mean, there are several, due to the time constraint and due to this being an introductory talk, I couldn't, in depth discuss, some of the examples that I presented earlier. They were inverse reinforcement learning example. And to discuss inverse reinforcement learning, first we'll have to cover the significant amount of mathematics to appreciate any of the IRL algorithms. So this is the reason why I couldn't cover the inverse reinforcement learning. Similarly, I couldn't do a justification to the mathematics behind the policy gradient methods, because again, the mathematics of policy gradient methods is too complex as compared to the value-based methods. And in this introductory presentation, it was not possible to discuss all those things. There are several deep RL algorithms which are not covered. For example, we did make use of deep reinforced algorithm in solving one of the real world problems. So I mentioned that our motion control framework had 5 RL agents. So one of the RL agent actually used deep reinforced algorithm actually to train. So I couldn't cover that as well. I couldn't highlight some of our IRL research that is targeted towards solving the level 4 and level 5 autonomy. Even the examples that I presented, the off policy or the off-shift policy, this is a kind of a task that cannot be learned with forward RL methods. I mean, there's no way you can learn with forward RL method unless you are working in a toy world like deep traffic. For example, if you're using a deep traffic simulator, which is a toy simulator, you can still do it, but for real world application, it is too difficult to use a forward RL approaches to learn such a control policy. Earlier, I also mentioned that it's very hard to design or engineer a reward function. So essentially, to summarize in one line statement, inverse reinforcement learning methods, they actually learn the reward function via the data. So usually, I mean, again, very crude essentially, basically, they learn from human demonstration. So there are human demonstrated trajectories actually, which we use to actually, learn the reward signals. And then basically we use, several of the algorithms in IRL and deep IRL framework to actually compute a policy for that, for the learned reward signal, and perhaps improve upon as well. I couldn't also cover the meta learning, the semi MDPs, and the abstraction methods. And interested readers can actually, independently look into these topics and can go deeper into any other topics that I've covered as a part of this presentation. Thank you.
Yeah. So thank you, Mr. Sanjeev. This was a very comprehensive talk. I didn't realize that you would be covering so much of maths as well. I thought it would be just but yeah, it was great. So people got some idea probably that how much math can be involved in when you start thinking about deeper levels or advanced algorithms in reinforcement learning. I think the reinforcement learning is a complete 1 semester course, actually even 2 semester course here. I think Dr. Shashi Shekhar Jha is here in this participant list. He is taking one course right now, in one of my students is attending this course. So yeah, so if others have any questions, then we can take questions for 10 more minutes. Yeah, hi Shashi. So you can take questions for 10 more minutes, and after that we can close. Yeah.
Yeah, I have one question.
Yes.
Sure.
So yeah, great talk. I enjoyed your talk. Actually, a lot of content even I'm going to use the way you have described. It was nice. So thank you for that. So what I want to ask is, what are some of the successes of your autonomous driving experience that you have seen in India, in Indian roads or some of the Indian setups?
Sure. So currently, if we talk about our autonomous driving technology, so we have arrived at a point where we have the capacity in terms of algorithms to enable high-speed navigation. Our technology can deal with very tight spaces, not just tight spaces, but tight stochastic spaces, right? With other agents, other obstacles in the environments being dynamic. And in one of the demo that I focused most upon during the presentation, that demo was done in 2017 in November, right? So their entire full video is on our website. So these are the capabilities that we had achieved, previously. In terms of the what our autonomous driving technology as a whole can do. So, for example, this planning is okay. Planning has been 70% of our research. Perception is roughly 25% of our research, and then the rest of our research is focused on combining our perception and planning abilities to actually come up with a novel autonomous driving paradigm which doesn't make use of what we call high fidelity maps. So, for example, in traditional autonomous driving, before an autonomous driving vehicle can navigate in an environment, the entire map has to be built, and that's a huge hindrance to scaling up autonomous driving. And this is one problem. So I started my research when I was a second year undergrad at IT Roorkee, and my focus was to learn, design motion planning algorithms that can deal with unknown environment scenarios, right? And since 2014, I'd been investigating very seriously this problem of autonomous driving without high fidelity maps. So currently, we have, in terms of algorithmic capacity, we are one of the 3-4 companies in the world who have attained this capacity to be able to perform autonomous driving without high fidelity maps. In fact, one of the portions of this talk I'm presenting at NVIDIA, basically a small talk at NVIDIA, where I present the perception component of this research to enable autonomous driving without high fidelity maps. We have already done demo on highway. Earlier, we dealt with a lot of mechanical issues in our vehicles. So most of those issues were either resolved by using some of the optimization techniques or using reinforcement learning techniques. And some of the glimpses of that I have shared in this talk as well, like how we are able to use the classical RL to get rid of some of the problems.
So can we say one follow-up question? Can we just say that if we take very structured areas, like our IIT campuses, or you have these army and military campuses, in those kind of very structured areas, the technology is ready to be deployed.
Yes. So basically, so you also have to consider that we are a startup, and we have been a bootstrap startup for the most portion of our startup life. And so, from proof of concept point of view, yes, our technology is ready. There would be scale up that we have to run. For example, when you design, let's say, perception algorithms for a POC, you may train it with few million images, maybe 1.5, 2 million images. But when you deploy in a commercial capacity, that few million will become few tens of millions, right? So these are, some of the contractual. So what we are essentially working on. So our goal is pretty straightforward. We want to design the technology that, number one, is able to deal with the level of stochasticity that is present in the Indian traffic dynamics. Once you solve this problem, you can take the technology and deploy it in North America, Europe, or any other environment for that matter. For example, one of the very special use case of our technology is the exact campus driving that you mentioned, and also the industrial autonomous robots. That is one of the very specific use case of our technology, and we are actually working on that to actually deploy it in a commercial capacity.
Okay, thank you.
Yeah, so Sanjeev, means I used to do a lot of robotics earlier when I was in my undergrad. That time we used to use these and just standard image processing. That time even I think RL nobody was talking about. But I was thinking about like if we think from digital electronics perspective, like you are from electrical engineering background, like as I see RL is something which you can talk as if like sequential circuits versus combinational circuits. As a combination sequential circuit, you have this memory which feeds back, and then yeah, probably the training is already done in that circuit, but something of that sort, right?
Sure.
Yeah.
Sure.
And some people here. Yeah, some people here have asked that what are some good materials would you suggest? I think Professor Sutton's, who is probably the guide of Mr. Sanjeev, is the most well-known name in reinforcement learning. If some other material Sanjeev can
So
suggest.
his book is the primer for reinforcement learning. For example, if you want to study reinforcement learning, that book is going to be a very essential ingredient. It will bring you to a point where you would be ready to read and understand the modern reinforcement learning papers. But again, that's a statement to make. You'd also need, significant background in machine learning to be able to comprehend the mathematics that is used in typical modern reinforcement learning publications. But that book, if you have a good machine learning knowledge, you can start focusing on that book, and it will bring you to a level where to gain more to gain more knowledge, you just have to read the research papers. So that book is a very good one. Other than that, I think there are some free lectures from Sergey Levin as well as David Silver from DeepMind, actually, which are tremendously helpful as well.
And can you talk about DeepIgen? You have another startup, DeepIgen also?
So DeepIgen is actually our deep education startup, right? For example, let's suppose if you want to gain the knowledge that is only taught at one of the top 10 graduate programs in the world, right? Let's suppose you want to study machine learning, you want to study computer vision, right? So DeepIgen is a platform that actually provides that level of education. So we have 3 different categories of courses: category 1 and category 2. So category 1 courses can be thought of as a full semester or 2-semester graduate school courses. And category 2 courses have sufficient theory, but they're focused more towards the practical application. So our goal with DeepIgen is to actually provide very deep cutting edge education, but with price that is 1/5 of the price that you would pay in a graduate school. And our goal is to bring that price to 120 to 110 range 2.5 years from now. So that's DeepIgen.
Okay. Questions? Okay. So, thank you, Mr. Sanjeev, for all this, such a great session. And I hope everyone enjoyed it. I understand that probably a lot of this material, many of the people who are here might not have of it, but I think that this gives you a subconscious, feeling of how much maths is involved and some indicators on how reinforcement learning works. And probably by using this background, you would be able to go through the materials which are there, through that book by Professor Sutton and other materials available on internet. You might be able to build over that. So thank you, Mr. Sharma, for joining, and I will be sharing this video with the participants under this. So this is already recorded, so those who want to go through this material again, they can do so.
Sure.
Okay,
Thank you so much for inviting me to give this talk.
Yeah, thank you, Mr. Sharma. Bye.
Yeah.
Okay.